Have you ever stopped to think that every number might have, well, a hidden code? A kind of numerical DNA that makes it completely unique? Well, today, we're going to crack that code. So let's start with a pretty huge question. If you could take any whole number and just break it down into its absolute most essential, indivisible parts, what would you even find? Let's find out. All right, our quest starts right now. We're going looking for those hidden building blocks that construct every single number we know. And the best way to think about it is like this. You know how in the real world, you've got all these countless complex molecules, but they're all built from a pretty small set of atoms? Well, it turns out mathematics works on the exact same principle. There's this special set of numbers that are basically the atoms for all the other numbers. So what are these mathematical atoms? They're the prime numbers. Let's dive in and see how these fundamental little units build literally everything else. First, we got to get a handle on the molecules. In math, we call them composite numbers. So a number like 6 is composite because, it's built by multiplying 2 and 3. Or 10 is composite because it's just 2 times 5. These are the structures we're about to break apart. And here's the cool way we do it, using something called a factor tree. You just grab any composite number you want, then you start dividing it by the smallest prime you can, which is 2. And you just keep going until you can't anymore. Once you're done with 2, you move on to the next prime, 3, then 5, and you just keep repeating the process until the only things you have left are those prime building blocks. And there it is, the unique code, the DNA, for 32,760 is 3 2s, 2 3s, 1 5, 1 7, and 1 13. This is what we call its prime factorization. And what's so amazing is that every single composite number has its own unique prime DNA, just like this. But here's where it gets really, really profound. This whole process of breaking down numbers, it's not just some neat party trick. It's actually governed by one of the most powerful, most important laws in all of mathematics. This is the big one, the Fundamental Theorem of Arithmetic, and it's really saying two things. First, that any composite number can be broken down into primes. We just saw that. But the second part, and this is the really mind-blowing part, is that this breakdown is totally unique. I mean, think about that. It's like a fingerprint for numbers. The number 32,760 will always break down into this exact set of primes and only these primes. Just like your DNA, its prime signature is one of a kind. There is no other combination of primes in the entire universe that will multiply together to give you 32,760. And the person we have to thank for first proving this incredible fact, for cementing this beautiful rule into the foundations of math, was the absolute legend himself, Carl Friedrich Gauss. Okay, so a number's prime DNA is unique. That's a cool fact, but so what? What can we actually do with it? Well, it turns out this one single rule lets us solve some really fascinating puzzles. All right, let's try to solve one. Imagine the number 4 raised to any power n. Could a number like that ever end in a 0? Like 10 or 80 or 520. Well, the clue is hiding in its prime factors. See, for any number to end in 0, it has to be divisible by 10. And that means its prime DNA absolutely must contain both a 2 and a 5. And this is just a beautiful illustration of the theorem's power. What's the prime DNA of 4? It's just 2 2s. That's it. So no matter what power you raise it to, the only prime factor it's ever going to have is 2. The prime 5 is completely missing from its genetic code, so it can never be divisible by 5, which means 4 to the power of n can never end in 0. And it's the uniqueness from the theorem that guarantees this with absolute certainty. But the theorem's power goes even deeper than that. We can actually use it to prove something that puzzled ancient mathematicians for centuries, the existence of these strange things called irrational numbers. So an irrational number is a number you just can't pin down as a simple fraction. The square root of 2 is the most famous example. We know it's a real number, but how on earth can we prove it's irrational? Well, we're going to use a really clever technique. It's called proof by contradiction, and it's wonderfully elegant. Basically, you start by assuming the exact opposite of what you're trying to prove is true. Then you just follow the logic down the rabbit hole until you hit a wall, a complete paradox, something that makes no sense. And if your logic was solid, it can only mean one thing. Your initial assumption had to be wrong. Okay, let's walk through this one carefully.
First, we assume the opposite. Let's pretend the square root of 2 can be written as a simple fraction, a over b, and that we've already simplified it as much as possible. Now, if we square both sides of that, we get 2 times b squared equals a squared. Look at that equation. It tells us that a squared has to be an even number. And this is where our theorem is so crucial. For a square number to be even, its prime DNA must have the prime number 2 in it, which means the original number a must also have a 2 in its DNA. So a itself has to be even. Okay, but it turns out if a is even, then b also has to be even. And that's the paradox. If both a and b are even, that our original fraction wasn't in its simplest form after all. We've just contradicted our own starting point.
So the whole point is, our initial assumption, the idea that the square root of 2 could be a fraction, led us straight to an impossible paradox. The only logical conclusion is that the assumption itself was false. The square root of 2 simply cannot be written as a fraction. It's irrational. So, from building every number to proving the existence of the irrational, the fundamental theorem of arithmetic shows how this simple, unique code governs the entire world of numbers. And that kind of leaves us with one final thought. If prime numbers really are the atoms of math, what other universal secrets are just sitting there, waiting for us to finally decipher their code?